Hello everyone, welcome back to lecture series on EM3 subject. For more videos like our today's video, you may check it into our playlist. In our today's video, we are going to learn some of the example which based on the particular integral. Already I uploaded the method and all this procedure into my channel. So if you are interested to see similar video, do check in my playlist. So let's get directly start our today's lecture with the example from particular integral. So actually I'm going to explain to you all. I'm going to explain to you all one of the property using example. Okay, so here we have first example d square y by dx square. We have first example here d square y by dx square minus 5 into dy by dx minus 6 times y, which is equal to 0. Okay, so we want the complete solution. Okay, complementary function plus particular integral. Okay, so we have to find out here, okay, what we need to find here, complete solution. Okay, we have to find out the complete solution. As we know that complete solution means it is a complementary function plus particular integral. Okay, that means we have to find out the CF. Okay, for this we have to find out the complementary function and particular integral. Okay, yes. So we are not able to find the particular integral here, as we don't have right hand side which is present. Okay, which is not present here, but it is okay. I will explain at the timing of a particular integral. Okay, now let's go for finding the complementary function. As we can see, our differential equation, it is second order differential equation, as we have highest power 2. So we write d square y by dx square as a d by dx as a capital D. So d square by dx square, which is equal to capital D square. Okay, so replace all these values here. So we'll get the d square y minus 5 dy minus 6y, which is equal to 0. Okay, so take to the auxiliary equation. Okay, so we write its auxiliary equation. We write its auxiliary equation as a d square minus 5d minus 6, which is equal to 0. Okay, so we have auxiliary equation as a d square minus 5d minus 6, which is equal to 0. Now it is just a quadratic equation, so it is easier to find out the roots for this equation. So let's find this root, or simply we can say that here we want the two numbers, their multiplication is a minus 6. Okay, their multiplication minus 6, so we consider the two number as a minus 6 into 1. Okay, minus 6 multiplied by 1, their multiplication is minus 6, and we want the addition for these two number as a minus 5. Okay, so we can see that minus 6 plus 1, which is obviously minus 5. Okay, so expand our auxiliary equation in the form of d square minus 6d plus d minus 6, which is equal to 0. Now see that minus 5d are written as just minus 6d plus d. So if you are going to add these two numbers, you will get the minus 5d. Okay, yes. So take d common from here, from first term, d under bracket d minus 6 plus 1 common from remaining term, d minus 6, which is equal to 0. So d minus 6, it is similar here, take it common, d plus 1, which is equal to 0. So as we can see here, we got the two root, d which is equal to positive 6 and d which is equal to minus 1. Okay, so these are the two roots for our linear differential equation. Okay, so now see that let's go for finding the complementary function. As we have roots are real and distinct, then we write it's a complementary function CF. Okay, how can we write complementary function? C1 e to the power m1x plus C2 e to the power m2x. As we have roots are real and distinct, then it's a complete solution. We write C1 e to the power m1. m1 means first root and m2 means second root. Okay, so m1 is a 6x plus c2 e to the power m2 minus 1 multiplied by x. Okay, that means c1 e to the power 6x plus c2 e to the power minus x. It is the complementary function for our differential equation. Okay, let's proceed with the particular integral. Okay, yes, as already we learn everything about the particular integral that we are going to apply it here. Okay, yes, let's go for finding the particular integral. Be careful here because this one is the first example based on the particular integral. Okay, so that example, we are a similar example we are going to solve it later, but this one you need to understand. Okay, yes, particular integral, we know that we write particular integral as 1 upon f of d into phi of x. Okay, we write 1 upon f of d into phi of x. This one is a particular integral. Okay, already we written that particular integral from the solution or highest nth power differential equation when we take into the auxiliary equation. Okay, so I explained this one in my previous lecture. So this one is a particular integral. Now we have to replace f of d and phi of x. Okay, now see that how f of d and phi of x are coming. Okay, f of d means the terms, our function in the form of a d. Okay, so this one is the obviously d minus 6 and d plus 1, it is our f of d. Okay, so if you are confused here, so you can consider this one as a d square minus 5d minus 6. Okay, this one is our f of d. Okay, and of phi of x. So what about for phi of x? It is a right hand side we have here. Okay, which is a 0. Okay, this one is our phi of x, as we don't have phi of x which present here in given differential equation. Okay, so as we don't have here, so we consider it as a phi of x as a 0. Okay, yes. Okay, let's go for the next step. So we have here phi of x which is equal to 0, as we have right hand side which is completely 0, and f of d we have to write it as the auxiliary equation. So f of d is the auxiliary equation for our given partial linear differential equation. Okay, so we write d square minus 5 times d minus 6. Okay, this one is our f of d. Okay, and obviously the similar meaning for this auxiliary equation, it is a d minus 6 and d plus 1. Okay, this one is our auxiliary equation. Okay, let's go for substitution of the value. Put f of d here, phi of x here, you will get the particular integral. Okay, so particular integral we write here 1 upon f of d. F of d is a d minus 6. Okay, f of d is a d minus 6 into d plus 1, and which multiplied by phi of x. What is the value for phi of x? Which is a 0. So we can see that particular integral, we get it here 0. We got the particular integral which is 0. Okay, and if particular integral it is a 0, then we write a general solution as a y of x, which is equal to complementary function plus particular integral. So what is the complementary function? We got it here, c1 e to the power 6x and c2 e to the power minus x. Okay, so c1 e to the power 6x plus c2 e to the power minus x. This one is our complementary function plus particular integral, it is 0. So this one is our complete general solution or complete solution for our given second order linear differential equation. Okay, yes. Now see that here we can observe one thing. So what we can observe here in our example, now see that when we have the right hand side for our differential equation, okay, or right hand side of our linear differential equation, it is a 0. That means particular integral always remain 0. Okay, so whenever you get the question in your question paper, university question paper, so if it represent one of the side is a 0, one of the side it represents 0, that means our given differential equation has particular integral, it is a 0. Okay, so that's it for this example. So these are important example, guys, asked in your previous year question paper. So nothing it is here, so everything it is completely easy. Okay, so I'm going to continue some more example, but before that I want you all to go for some of the homework questions. So here we have two example, first one and second one. Consider this example for your homework and answer me their solution in my comment section. Okay, so you all have to solve this example, so you'll get the good practice. I hope you all have understood this example. So now afterward we are going to solve some examples where both sides are present. That means 0 it is not there. Okay, that means left hand side and right hand side, both sides are non-zero. Okay, in such a case we have to find out the particular integral. Okay, now in this case it is not that difficult. We have to apply some basic results. Okay, that in my previous lecture I explained to you all 1 upon d minus a e raised to x, 1 upon d plus a e raised to x, or 1 upon d e raised to x, this type of the results. So you must have to remember these results in order to solve the particular integral. Okay, so that's it for my today's lecture. So this one is the today's lecture. I explained here why we define particular integral, why we cannot define particular integral when we have one of the side is 0. Okay, that means it is we define it here, but if the one of the side is 0, that means particular integral it is 0. Okay, so this is the reason why particular integral goes to 0. So I hope you all have understood everything here in my today's lecture. Okay, in my next lecture we are going for another example that right hand side and left hand side, both sides are non-zero. Okay, I hope you all have understood my today's lecture. So thank you everyone. Thank you guys for my today's lecture.